As a product engineering manager, my biggest challenge is to improve yield and get to entitlement at a much shorter runtime. And what I see with the advanced FinFET technology, by the time the fab starts, the foundry partner starts manufacturing the wafer to physically getting the wafer, it will take between 4 to 5 months. So if I have to make an impact on the yield, usually most of the defects don't get cleaned up in one go. So you may have to need 2 or 3 cycles. So for me to actually attain that yield improvement, it can take a year or so. So how do we shift that left, and how do we squeeze that schedule much faster? That's where Scan Diagnostics come into the picture, because you get precise coordinates to exactly understand where the defectivity is located, as long as you exactly know and you pick the die that you're looking in. We can start off at the scan pattern level itself and figure out if there is a specific pattern that is showing systematic issues. Then we can go one step lower and figure out if there is a particular cycle that is systematically failing across multiple die. The third level is to look at the fail files across multiple die to figure out, again, if there is a systematic issue. That way you can go and get to the systematic die or problem much quickly. Most of the times, if these 3 levels are not enough to figure out a layout level sensitivity or a backend level related sensitivity, or a particular cell, a standard cell that's popping up because of some interaction of a layout and the process, that's when you can actually use Scan Diagnostics to find those signatures. So it really depends on whether you're targeting a layout issue or a pure process defectivity issue. Scan Diagnostics can help you get that answer. When the fab produces defects, some of them can be categorized as random defects and some of them are systematic. So it's usually a challenge to figure out within those random defects, is there a systematic signature that you have not seen in the sample size that you have analyzed? That's where TYI with RCD feature comes into picture. The TYI tool in general has pretty neat dashboard that allows you to analyze based on symptoms, based on suspects, based on the instance count, based on the location of the wafer, and based on the layout, or depending on whether it's a particular cell type. So you have an entire portfolio of analysis views that are already predefined in TYI. For you to use RCD, of course, you have to set up to enable all those constants before you start your diagnostics. That way, you are better prepared for systematic versus random defects. Identifying the right fault models that we need to use for the scan defectivity screening has become a biggest challenge because of the process integration issues and the process changes that we have seen in the lower FinFET nodes. So we've been working with our EDA vendors and our foundry partners to determine the optimized set. Let's say you solve a challenge. The next piece is how do we look at the data? Traditionally, we've been having the production data and the diagnostic data sitting in silos and not talking to each other. We believe there is tremendous value in mapping the production data with the parametric data, your sensor-related data with your scan diagnostic data and your memory diagnostic data to get a comprehensive view of the defect portfolio that is currently sitting in production, so that you can pick the right die for an EFA or your PFA. As automakers move towards software-defined vehicle architecture, where the production, where the product development life cycles are shrinking from 1.5 years to probably 1 year or 8 to 9 months, how do we still go and maintain the outgoing customer quality will be a big challenge for us. The other area that I see that the industry has not focused much is on the stress coverage, where how we can quantify the stress that we do as part of production and how do we close that gap is yet to be seen.